Thanks, Tim. Okay, welcome everybody to this week's Australian Geometric PDE seminar. Today we have Sathya Rengaswami, who's going to be talking about ancient and soliton solutions to geometric flows. Over to you, Sathya.
Hi everyone. Let me. Am I able to share my screen? Oh yeah. Okay. So I'm able to. So let me bring up my document. So thank you to the organizers for giving me the opportunity to talk about my research here. I'm like really excited to share with you some of the some of the things that I've found like in my research, and like hope to like have a like stimulating conversation with you guys. And like if you have any questions at any point, please stop me and ask away. And also like if you have any suggestions for or like ideas for me to think about, like regarding like related problems to what I've done, I'm also like open to discussing those sorts of ideas. So let me get started. So what I'm interested in is like, so generally speaking, I'm going to be talking about like extrinsic curvature flows and two specific kinds of solutions that I had worked on in this setting are translators and what are called pancake solutions. I did some work on, and I want to discuss those ideas here. So maybe just very quickly, I'll not belabor the point here too much, because I think like all of us know what's going on in curvature flows, but just maybe a very brief introduction. So the setting here is like I have I think of my ambient space as being Rn plus one, and then I just have let's say I have a manifold here. The way I'm gonna deform this manifold is like by giving it a speed which is proportion, like which is a function of its curvature here. So I'll say like minus f of the curvature vector times the normal vector. So the curvature vector is just the n-tuple of principal curvatures, and so this f I'll refer to as the speed function. N is of course like the outward pointing normal, and so the main example is the curve shortening flow, right, where you have curves in the plane, and so the speed is given by minus just the curvature itself times the normal. That's the classic extrinsic flow. And so I guess like the most trivial solution in this case would be just the line in sorry, for the plane, and the trivial solution is just the line, right, which doesn't do anything. It just sits there. There are also some other basic solutions which I'll just show pictures of. So we have like a family of shrinking circles. So they stay circles and just converge towards their center. We have what's called the so-called Grim Reaper, which moves by translation. So this guy lives inside some strip of like finite width and just moves by translation. That's it's called the Grim Reaper. There's this the so-called Angenent oval, which is like kind of looks like two Grim Reapers stuck together. So very like at very negative times, the ends kind of look like two Grim Reapers. This one and these two. kind of look like Grim Reapers. And as time approaches 0, they just start looking more and more like circles and then collapse down to the point. I mean, to the center. And so these are essentially what are examples of these things called ancient solutions, which I mentioned in the title of my my talk, right? So what I mean by ancient solution, just for completeness sake, I'll define these things. So ancient means like I want these solutions to be defined on some for all past times, and beta can be positive or sorry, it can be finite or positive infinity. It doesn't matter. So the reason why we study ancient solutions is like if you so there's like if you zoom in near singularities, you see these showing up as limits. So that's the so we call them like blow up limits, and they like if you zoom in near singularities, you see them. And the 4 examples that I gave you so far, they're all ancient solutions. The circle, the straight line, and the other, the Grim Reaper and the Angenent oval are all examples of this. Here's something nice about the curve shortening case. So there's like, as long as you, I mean, if you look at ancient solutions, there's lots and lots of them, but if you impose a convexity condition on them, it turns out that the 4 examples we saw are the only ones. So this is due to like some work in 2010 by Daskalopoulos, Hamilton, Session, who basically were discussed the cases where, like, if these are embeddings of the circle, then they proved that you have to be one of these 2. And then the non-compact case was completed by Borney, Langford, Tinaglia, and that was published in 2020. So that takes care of the other 2 cases. So eventually, I'm going to be interested in the same convex ancient solutions, but to higher dimensional flows. That's why I bring these up, and also, so I'll be using these objects in my constructions as well. So a related kind of flow is what's called the kappa to the alpha flow. So here it's almost like the curve shortening flow, except your flow speed now is not just kappa, but kappa to some power alpha. And so interesting things start happening when you put an alpha's power here. So I think like one of the big results in this in this kind of flow is by Professor Ben Andrews, who in this paper classification of limiting shapes for isotropic flows, he looks at homothetic solutions that just contract while preserving their shape. So he studied these kinds of things, and he actually noticed something pretty interesting, which is if alpha is bigger than 1/8, then the flow is actually strong enough to, I mean, rigid enough to where only round shrinking circles are the solutions. Except in the alpha equals 1/3 case, that's like the affine case, you also have these ellipses showing up. But for alpha less than 1/8, what seems to happen is like you have these solutions with k-fold symmetry is also showing up in addition to the circles. So kind of like these like polygonal kind of objects. I mean, of course, they have like smoother looking corners, but you have objects like this, which evolved by just homothetic shrinking. So what this seems to suggest is like,
are these solutions actually smooth?
Yes, they are.
Okay.
Yeah. Sorry, the way I drew it was like, so they have like, and so I think also what the paper mentions is that like as alpha goes down to 0, these shapes converge to polygons, and as alpha converges to not 1/8, but I think like if you have a k-fold symmetric solution, as if alpha converges to, I think, 1 over the k squared minus 1, the solution converges to a circle. Or sorry, I think that's not right. If alpha converges to 1/8, these solutions converge to circles. So what's interesting about this is there seems to be like a very interesting way in which the exact speed function that you have, right, kind of influences the way that solutions look. And so in general, this is the kind of thing that I'm interested in. Like, so how do the properties of your speed function affect the shape of your solution? So that's kind of like the theme of my my research so far. So I'll talk about like the situation in higher dimensions. So I think like mean curvature for flow in higher dimensions, that's like the most studied flow, right? So the F here is just the sum of principal curvatures. The Gauss curvature flow is also pretty well studied. So where there, like the F of kappa is just kappa 1 times kappa 2 times this, the Gauss curvature. So this is like very commonly studied in the literature, but that's not all. There's this interesting flow called the inverse mean curvature flow, which is like your flow speed is the reciprocal of mean curvature. And this seems to expand solutions to like very large, like, I mean, at least if you start with something that's like topologically a sphere and like convex, I presume, like this flow will expand you to almost like circular spheres, I mean, or like almost round spheres, like of very large radius, and and so the application is like comes in a very interesting area, which is general relativity. So they used something called the Garak monotonicity formula to prove the Penrose inequality using this flow. So again, we have a lot of applications to general curvature flows, not just mean curvature, but other kinds of flows that can be interesting and useful. So that's kind of like a reason why I became interested in the subject, because like I want to know, so how do the properties of the speed function influence the shape of your solution? So this is how I abstract my speed function. All the examples I've shown you, right? So if you multiply each of the principal curvatures by some number lambda, then the speed itself scales by lambda to some power. So this condition is called the homogeneity condition, and so it's like lambda to some alphath power, right? So for instance, the mean curvature has alpha equals 1. Gauss curvature has alpha equals k. Equals the dimension. This inverse mean curvature has alpha equals -1, and so on. That's the homogeneity condition. And like none of these speeds care about like the order in which you put your principal curvatures, right? So that's another condition I put on like abstracting these speeds. So that's like the second condition here. And I want these speeds to be like contracting speeds. So meaning I want the flow to be flow speed to increase when I increase one of the principal curvatures. So I call it ellipticity, and this in general ensures that your solution contracts down to a point and so on. Like usually if you start with like something that's convex and sphere, like a topologically a sphere, like this condition will ensure that you contract down to a point. This is like a good kind of speed. And also, if my principal curvatures are positive, I want my speed to be positive as well. So those are the abstractions I'm putting on my speed function. So anything that satisfies these conditions, I'll call an admissible speed. So now, so the next thing is like I want to study like the situation of translators in these speeds, right? So just for completeness, I'll define what a translator is. So it's so here's your ambient space Rn plus 1, and so this guy uh, uh, so let's say like M is a shape, so we call it a translator if it like if at future times it just looks like a translated copy of itself. So this is like M, like let's say T2 and T1, and so the way it evolves is just by translation. Not every point moves at a fixed velocity, but as the overall shape is maintained. And so so they are like I'll not go into the derivation of this equation, but in general, your translating solutions they obey this PD, which is your speed of all the principal curvatures is equal to minus of this translation direction, which I call E. So I'll call this translation direction E. E dot inner product with the normal at that point should equal the flow speed. So this is in general an elliptic PDE. At least for the speeds that I consider, this is an elliptic PDE. So now, what is it that I'm specifically interested in? So you may actually, like if you work in mean curvature flows, you might know this thing called the Bol soliton, which is like so it has like a radial symmetry, and so like down here is Rn, and like this is like the translation direction, which I'll call R, and so this is something that evolves by translation. So the fact that these things exist, this goes back to 1994. So this is work by Altschuler and Wu. They showed that these things exist, not just the radially symmetric ones, but like more general ones without any symmetry also exist, and they use like like existence of solutions to like Dirichlet boundary value problems and that sort of techniques. But the explicit work on the ones with radial symmetry, that was done in 2007 by Clutterbuck, Schnurr, and Schulze. So this is and so their tool is like, because you have this radial symmetry, right? They were able to use ODE analysis to actually study this solution. So they get existence uniqueness for arbitrary dimension, but also what's interesting is they are able to tell you what the shape looks like, shape of this Bol soliton, at least asymptotically. As you go out to spatial infinity, they're able to describe the shape. They're saying basically your Bol soliton kind of looks like a paraboloid as you go out to spatial infinity. So this is like this is in mean curvature flow, I wanna say, because the situation in other kinds of flow is like maybe the asymptotics might not be the same. Maybe like there are other different properties too, which I wanna talk about now. So if you're not looking at mean curvature flow, if you're looking at powers of Gauss curvature flow, right? You're taking Gauss curvature and taking alpha over nth power of it. So the way I write it this way is because this is an alpha homogeneous function. Because k itself is n homogeneous, so I need to take nth root of it to make it alpha homogeneous. Okay, so here the situation is pretty different. The work on this was done by John Urbas in 1998, and so like he uses like Monge-Ampere equations, and again he's looking at like arbitrary domains, not even looking at the radial case, and so he's able to show existence and uniqueness of these solutions, and then the rotational case comes out as just a corollary. Like if you study the like he's able to take like just arbitrary domains omega in Rn and study the translator equation on these domains. And the radial ones, how you get them is like if you just insist that your omega be radially symmetric, then your solution also has the same symmetry. So that's how he concluded that these things exist in for powers of Gauss curvature as well. And so let me just talk about like the ones with radial symmetry, because that's the one that I studied. What seems to happen is like here's something like a kind of like a bifurcation based on like how much your alpha value is. So it turns out that if alpha is less than or equal to n over 2, then it kind of looks like the bowl soliton, in the sense that this bowl is kind of defined on the entire Rn as a graph. But if alpha crosses n over 2, like if the alpha is like large in general, then this doesn't exist on the whole as a graph on all of Rn, but only as a graph on some finite radius ball. So alpha less than or equal to n over 2, you have these things that are what we refer to as entire solutions. They are defined on the entire plane and also sweep out the entire ambient space. And for alpha bigger than n over 2, what seems to be happening is like you have these solutions sitting inside some finite cylinder of finite radius. Okay, so this is like just background on like what work has previously been done with these solutions, right? So eventually I want to study these things in like the complete general setting and see when are your translators like entire solutions like this one, and when are they defined on when do they live inside a cylinder? And so that's something a question that I was interested in. So here's my finally I get to my first result. So what I found is that if like you take an admissible speed that I mentioned previously, it has all those nice properties, then you always have a like what it's like bowl type soliton. So the bowl soliton is like the name given to the solution of mean curvature flow. So this is like something that looks like a bowl soliton, but defined for a general flow I call a bowl type soliton. And so these things always exist for the class of speeds that I consider. And then there are also convexity comes out as a pretty easy corollary. Regularity is also the like standard PDE theory. If your speed function is ck alpha, then your solution is like 2 orders of differentiability better. This always this works out pretty nicely. Okay. If there are any questions, please feel free to stop me at any point. So let me talk about the details now. So here's the nice bifurcation in the kind of bifurcation that Darbus found for in Gauss curvature flow, right? So what I found is that regardless of like what your speed is, right? If the homogeneity is small, like less than 1/2 to be precise, then this bowl type soliton, right, is always an entire graph. It's defined on all of the plane and sweeps out the entire space. So people already knew about this for in the case of like the kappa to the alpha flows for plane curves, right? People already knew about this result in plane curves, but it also turns out to be true in for completely general flows in higher dimensions. So then for higher homogeneities, the situation is a bit more delicate. So we need some more definitions. Okay, so so what I want to talk about is like let's consider just a. So I want to classify my speed into two types based on whether this just usual cylinder, right, is a stationary solution or if it shrinks down to a line. Okay, so this guy will shrink down to a line if this condition is satisfied. E is just an n-1 tuple of ones. So if like n-1 of my principal curvatures are not non-zero, or rather even if one of them is non-zero, I must have that my speed is not non-zero. So then I call those speeds non-degenerate speeds. And if my speed vanishes, even like when one of my principal curvatures vanishes, I call it a degenerate speed. Okay, so so here's that cylinder condition that I was talking about. So the cylinder is a is a stationary solution precisely when you have a degenerate speed. Okay, so for instance, the Gauss curvature, this vanishes when one of the principal curvatures vanishes, right? I'm sorry, the Gauss curvature. And the mean curvature doesn't, like, for the mean curvature to vanish, like you need all the principal curvatures to be zero, or like some to be negative, some to be positive. It's so okay. Then what does this have to say about both solitons? So it turns out like if I have a non-degenerate speed, it turns out that I immediately get that my bowl soliton is an entire solution. Okay, and not only that, it's actually we can also know what its asymptotics are. Okay, so this is in general not going to look like a paraboloid like the mean curvature case, but the mean curvature case is kind of like a particular case of this result, because if I put alpha equals 1, which is what the homogeneity of the mean curvature flow is, you do get a paraboloid. Okay, so okay, so this result says that this phenomenon is like very general, and like your holds for all homogeneities. So that was like my main result, and then like so. Okay, so far, what's the situation? I have that if alpha is less than or equal to 1/2, that means your solutions are always entire. And regardless of alpha, if my speed is non-vanishing when like at least one of my principal curvatures is non-zero, then again I have a entire solution. So then, when do we get non-entire solutions, solutions that live inside cylinders? That's like is even more delicate than this. So I'll discuss that now. Okay. So maybe I'll give an example of this. So here let's talk about the degenerate speeds, where the speed vanishes when one of the principal curvatures vanishes. So maybe I'll take the Gauss curvature example. K equals just Kf, like, let's say the principal curvatures are kappa 1, kappa 2. This is just the product. And so if let's say I have the constraint equation that the K equals 1, then I may actually able to solve for one of the principal curvatures in terms of the other. So for instance, like a kappa 1 is just the reciprocal of the other one, right? Or in higher dimensions, maybe I have like I mean, if I also have radial symmetry, then this is just going to be kappa 2 to the n minus 1. So sorry, it's 2. So I'm always able to, like, if I have a constraint equation on my speed, then I'm able to solve for like one of the principal curvatures in terms of the other principal curvatures, right? And the first one is different from the other n minus 1s. The other n minus 1 ones, due to radial symmetry, they're all the same. That's why I have this n minus 1 tuple of ones here. So okay, and so what happens is, so in general, what happens is if my f of like x comma y equals 1, then so I mean, just by the assumption that the speed is like increasing in each of the slots, I can actually solve for my x in terms of y. X can be so so then it can also be shown that can also be shown that as y goes to infinity, just to balance out, like, your x has to converge to something finite, right? Some okay, so then you have two cases. Actually, you can also show that this is positive. So okay, so if as y goes to infinity, like if my principal curvature x, if it converges to something something positive, I have one situation, and if it converges to 0, I have a different situation. So in the Gauss curvature case, you can see that if my kappa 2 goes to infinity, my kappa 1 goes to 0. Right? So it falls under the second case here. If you want an example for the first case, then there's what's called the harmonic mean curvature flow. That's another example I'll give you now. So the harmonic mean curvature is like so if I have the constraint equation that then I can just explicitly solve for my kappa 1 in terms of kappa 2, like that. So sorry, kappa 2. And so as kappa 2 goes to infinity, kappa 1 converges to 1. So that's the That's the other kind of. So we have the two cases, and so my next result is okay. So if you have a high homogeneity, and let's say you have also that the speed degenerates at the boundary of the positive cone, then if you are in the if you're in the case that if you're in the case like the harmonic mean curvature flow, then we have that the solution actually lives inside a lives inside a cylinder. Okay, so that's the it's one of the results, and so then the last case is like, okay, so what happens if this quantity x star that I define is 0? Then also we have a condition that tells like when exactly do you have entire solutions and when do you have non-entire solutions. So here what happens is like, so in general, I guess, so in the constraint equation that f of x y equals 1, as y goes to infinity, x is approaching 0 is what my situation is. So if I have two theorems here, which I mean two conditions here that say that if as y goes to infinity, if x goes to 0 really quickly, which I give a precise condition for here, like how as to how quickly it must go to 0, then if it's too quick, then we have that the solution is the entire solution. If it approaches 0 kind of slowly, that is like if it converges to 0 slower than y to the -2 alpha minus 1, then you have the your solution is lives inside a cylinder. Okay, so it's like an almost complete classification of flow speeds for which like when is the solution entire and when is the solution, like when does the solution live inside a cylinder. I feel like I've been talking for a bit. Like, any questions so far?
Yeah, quick question about the conditions on F. So
Yeah.
you're just assuming homogeneity here, really, is that right? You haven't assumed anything additionally on F?
Pretty much. Like I assume the monotonicity as well, that the FB increasing with respect to each of the principal curvatures.
Right, it's got to be a parabolic equation.
The symmetry condition, I think, can be waived. Like I just put it in there because like it's a feature of all the well-known examples of speeds, but I don't think it even needs to be symmetric. You can I think you can still prove this theorem without symmetry. Okay, and so what's so how does this connect to the literature? Remember, like I mentioned how like Urbas finds like a bifurcation condition for alpha. Like this is exactly analogous to what he found in kappa to the alpha flows, but I'm able to show it like for like a more general class of speeds, which reduces down to exactly this condition when the flow speed you're looking at becomes k to the alpha. Okay, then we'll move over to the other kind of solution I'm studying as well, and so so for that I'll just mention this important like dichotomy that exists in mean curvature flow. This is what makes it makes what I'm about to say kind of interesting. So here's what's known as like Wang's dichotomy in mean curvature flow. So these convex ancient solutions that I'm studying, so they only come in two flavors. One is that they that they sweep out all of space, which is like what we define as a entire solution. So they either fall into that case, or your solution has to lie inside some sort of slab region. So let me go back to the curve shortening flow and show you that this is actually something that we observe in curve shortening as well. So I told you that the convex ancient solutions, they only come in 4 varieties, right? One is the shrinking circle. This is entire, like sweeps out all of the plane. This is contained in a strip. This oval is also contained in a strip. And the stationary line, that's also, I mean, you should take like a pair of stationary lines in order for them to bond a convex body, and still again, the solution lies in a strip. So, and like Wang was able to show this for in higher dimensions as well. If you have mean curvature flow and convex ancient solutions, then they always fall into these 2 types. And so I've kind of talked about like what's happening in the entire situation. Like I've found examples of translators that satisfy that. So now I'll talk about like solutions that lie inside a slab region, which is, by slab region I mean like Rn times some interval AB. This I refer to as a slab region. So so in these slab regions, what we have is like what are called pancake solutions, which is the general name we give to any solution that that just lies inside a slab and is also convex ancient solution lying in a slab is called a pancake solution. And so in the case of mean curvature flow, Shuja Wang was able to show in 2011 that these kinds of objects exist, like ones with radial symmetry, without radial symmetry. He approached it through PDEs, and he was able to like show that these very general pancake objects exist. But like the more like explicit construction was done by Borney, Langford, and Tinaglia. I think this was 2019, if I don't know. I'll have to check this one, but I feel like it's 2019. But is that right, man?
I think we're still waiting for it to appear, so I'm not sure what the correct date to put on that would be.
Okay. Okay. So so the radially symmetric ones, they Borney, Langford, and Tinaglia, they gave an explicit construction for how these things are constructed. So what they, maybe I'll just remark what their approach is. So what you do is like you take these Angenent ovals of curve shortening flow, and then so you revolve them about their short axis, and then you let them flow by mean curvature flow. So you have your Angenent oval, and then so this is the short axis, and then you revolve it around this axis, and then just let this object flow according to mean curvature flow. Now it's not gonna stay an Angenent oval because of the extra dimensions you added. The extra dimensions also contribute to the speed now, and so these won't remain Angenent ovals, but they kind of look like Angenent ovals. And what you do is like you take a limit as these for, let's say, for larger and larger. Okay, so as a so once you take that limit, then you kind of like use an Arzela-Ascoli type argument and infer that there is a limiting solution which lives inside a slab region and has all the radial symmetry and the fact that it's an ancient solution and so on. And the nice thing about this approach, this explicit construction, is also now you can infer what the asymptotics of this object are. It turns out that so let's say so this is like, maybe I'll draw it for like a so one more time slice of this object. For a previous time it looks like that, and so let me call this oh, excuse me. Yeah. So let me call the distance from here to this axis, right? Let me call that r of t, and so what this this explicit construction lets you do is it lets you estimate this radius as a function of time, at least as t goes to minus infinity. And as you look like further and further back in time, you kind of get an asymptotic equation for the radius of these pancake solutions. So it kind of looks like the highest order term is like a linear term. The next term in the asymptotic expansion is a log term, and then lower order terms. So so as time goes to minus infinity, that lower order term just converges to a constant. So this is in mean curvature flow, and I tried to repeat this same procedure in general flows. So what we do is like we take again a admissible speed, and I want it to be like non-degenerate as well, which is the f of like the speed is non-vanishing when one of the principal curvatures, at least one of the principal curvatures, is non-zero. So this time, I'm looking at only one homogeneous speeds, because like, I mean, eventually the hope is that I can do this for all sorts of speeds, but for now, the theory of one homogeneous speeds is like, there's a lot of literature available, and so for now I'm just focusing my attention on the one homogeneous speeds. And so what I'm able to show in this case is like I am able to construct these sorts of pancake objects by doing the same thing, taking Angenent ovals and then letting them flow not by mean curvature flow, but a flow according to the speed that like a speed that I prescribe, which is just a general admissible speed. And so these I'm able to apply the same, like, like take limits of these things as the ovals get bigger and bigger, and do the Arzela-Ascoli argument, and I am able to show that these objects exist. Uniqueness is kind of more delicate. I'm not able to show uniqueness yet. That's something I'm working on. But here is something I am able to say about these solutions. It is the asymptotic expansion kind of looks the same. For, let's say there are like more than one solution, but every solution has this asymptotic expansion. The radius of these pancakes, the first order term, like the highest order term, is a linear term. The next term is a log term, and then and the next the one after that, like I can bound by a constant. So this is and so C1, C2 are not just general constants, but they're actually, you can actually work out exactly how much their value is based on the speed function that you're talking about. So I think that kind of puts us at the end of my time. So so I guess like as far as like the discussion, like I'll cut it there and just take questions from here.
Thanks, Sathya. Thank you very much.
Thanks, mate.
Worries. Yeah. If there are any questions, please jump in. Well, I have one or two while you guys get your thoughts together. Do you, in the degenerate case for the pancakes, have you thought much about what might be different? I expect things to be different, but I haven't thought about it that much. So in a similar way to that, you have this range of behavior for these bowl solitons, where now they're defined in cylinders for different homogeneities and degeneracies of the speed. Do you expect to see something similar for the pancakes? Your microphone's off, Sathya. Sathya, your microphone's off. Sorry.
Oh, excuse me. So I think that these pancakes might as well exist, but I think this construction is not going to give me an answer, because like these Angenent intervals, as I talked about, like as time goes to -infinity, they converge to these Grimm reapers, and so like if you just look at focus on the tip, it's kind of going to look like Grimm reaper cross with a line, right? And for the degenerate speeds, those things actually don't move. Like if one of the directions is flat, then the principal curvatures don't move those objects anymore. So I don't know if the same construction is going to give me a solution. Maybe I'll have to look for like other ways to construct these objects. Higher homogeneities, well, in kappa to the alpha flows, I think Theodora did some work on these solutions that exist for like convex ancient solutions to kappa to the alpha flows. So maybe I'm able to revolve those objects and flow them and try and get a convex ancient solutions to higher homogeneities by working on those objects.
Right, that's a good point. Yeah, I don't have a good intuition for the different homogeneities, but yeah, maybe you expect something similar for high homogeneities as you get for the bowl. Interesting.
I mean, maybe if I can show that, like the Andrews result, like if you have very small homogeneity, maybe I do get these like ones with like k-fold symmetry and so on. That would be interesting to see.
Absolutely. Thank you. That answers my question. If anyone else has any,
I'll jump in with a question. You discussed uniqueness results for rotationally invariant translators. Is that right? So I'm guessing that the techniques that went into demonstrating that involved writing out a differential equation for what these solutions have to satisfy, and then studying. I wondered if you could give us an indication of what this differential equation actually looks like.
Oh, sure. Let me show you what the translator ODE looks like. 1 second.
It is an ODE, but it's kind of gnarly due to the generality of the.
Yes, I'm quite interested in seeing how gnarly it is.
Okay, so remember, like my translator equation kind of looks like this. It's an elliptic PDE, but once I impose that radial symmetry, then I actually get a. Okay, so also for radial graphs, you're able to work out the principal curvatures explicitly, right? As functions of u prime and u double prime. So your ODE kind of looks like this. And then so you solve for the first slot using the implicit function theorem, and then your ODE kind of looks like this. So G
Oh,
is
okay.
like the function that solves for the first slot in terms of the second slot and the right-hand side.
So if I understand correctly, it is a second order thing, but you make it a first order thing using homogeneity.
So the fact that I use is like U never appears on its own, like only U prime and U double prime show
I
up.
see, right. Yeah.
So I just set U prime equals V.
Okay.
And
Yeah,
and so
that looks like a fun equation.
yeah, and then so all the existence and uniqueness basically follows from existence uniqueness of solutions to this equation. And also the question about like when are these things defined on like finite balls, and when are they entire, that also reduces to the analysis of this ODE. So if this ODE blows up, like as R approaches the radius approaches some finite number, that corresponds to solutions living inside cylinders. If U is defined for all values of R, then that corresponds to an entire solution, and so on.
Yep. Awesome. Cool. Thanks.
That comes down to a barrier argument, if I remember correct. Is that right? Or is there a bit more to it?
Yeah. So I mean, like when you study ordinary differential equations, let's consider like the simplest equation, V prime equals V to the theta, right? So there is like a, I mean, let's say V of 0 equals some, well, I don't know, like V of epsilon equals V of delta equals some epsilons for some positive numbers at some positive number delta. Then this this equation blows up if theta is bigger than 1, like blows up in for some finite value of R is if theta is equal to 1, and then this is entire if this theta is less than or equal to 1. So the question of entireness, non-entireness basically comes down to if the right hand side is comparable to V to the theta, where theta is bigger than 1, then it has to blow up in finite time and so on. Finite radius.
Right. Thanks, Sathya. If there's any more questions, we could probably take one more, but if not, it is after 12, so I'm sure we're all getting hungry. So thanks again, Sathya.
Yeah, thank you for the opportunity to like for me to talk at this seminar. This was fun presenting my research, and look forward to seeing you guys in further meetings.
Cool. Thanks for speaking for us, Sathya. It's good to have you.
Thank you. See ya.
I'll stop recording now.